Okay, in this video we are going to see regarding the equilibrium of a 2D differential element, a two-dimensional differential element, okay, which is the part of theory of elasticity and plasticity. Okay, to know the equilibrium of a 2D differential element, first of all we have to consider a element which is in the shape of a square type of shape. Okay, it is not exactly square type of shape, it is the rectangular type of shape or any element you can assume. Okay, any shape of the element you can assume, you can derive the two-dimensional differential element. Okay, two-dimensional differential equation for that particular element. Here I am assuming one element. I have taken one element from the continuum or a continuous solid body, and I assigned stresses. You can see here sigma x, sigma y, tau xy and tau yx are the stresses of the element. Okay, I assume the stresses acting this particular body are the related to the normal stresses as well as shear stress components. Okay, are the function of xy directions but do not vary throughout the thickness. In the z direction there won't be any considerable thickness. Okay, we used to neglect the thickness in that direction, and that the other stress component are zero. Okay, then sigma z will becomes zero. Why? Because thickness of this body are we are assuming as zero. Okay, and also assume that the x y, or we can say f of x and f of y, components of the body forces per unit volume. Okay, these are the body force components. Okay, fx and fy are in, and these two are independent of z, and that the z component of the body force fz will be zero. Okay, the in the z direction, in outward direction, if you see outerward direction, the z force fz will be zero. Okay, the applied force will be zero. Because of negligible thickness, we used to take stress will be zero in z direction, as well as if stress is zero, then force will be also zero. Okay, now taking a moment of the force about the lower left corner of the lower left corner of the element, and I am going to equate this one to zero. Okay, if you want to see this one, you can go in the next slide. Here you can see this is the element, okay, which is carrying different stresses, and this is the, I'm going to take moment about this point at this corner, and the stresses will be sigma x, which is acting near to the x-axis. Okay, sorry, near to the y-axis, and it is moving in the negative x-axis direction. Okay, the sigma x is normal stress, sigma x is moving in negative x direction. Okay, whereas here stress is sigma x, and when it is moving towards the x-axis, stress will be increases. Okay, at depth of delta x, the increase of the stress will be this much, dou sigma x by dou x into del x. Okay, this is the increase of stress for this particular length. Okay, for this particular length dx, the increase of the stress will be this much, and total stress acting at this particular point will be sigma x plus dou sigma x by dou x into del x. Okay, this is normal stress which are acting on this particular plane. Okay, which is the plane is having the area of del y into unit thickness 1. Okay, then this one will be the normal stress. Okay, and another normal stress will be, we can see here sigma y, which is acting in negative y direction, and similarly this stress will be increases in when it is moving towards the y-axis, along the y-axis. Okay, there also same thing, same amount of will be stresses increases for this particular height del y, and we can see here increase of the stress, total stress on the y-axis will be sigma y plus del sigma y by del y, sorry, dou sigma y by dou y into del y. This is the stress which is acting another side of this particular selected element. Okay, and similarly we can see here shear stress components. As we see here, two shear stress components, tau xy and tau yx. Okay, and this shear stress component tau xy will be acts on this particular plane, which is having the length del y and thickness unity 1. Okay, in this surface tau xy is acting at this particular surface, counterpart of this surface tau yx is acting. Okay, similarly if we see shear stress component, increase of shear stress, tau yx will get increase. You can see the increase of the stress will be here, and similarly tau xy will be increases dou tau xy plus dou tau xy by dou x. Here dou x will be there, not dou y, dou y. Here we have to make a correction here. Dou x is there actually. Wait a second. Okay. Dou tau xy by dou y into del x will be the increase of the shear stress. Okay, here we can see two shear stress components, and here we can see two shear stress components. Whereas these all the stresses will act if we assume the forces experienced by these all stresses will be acting through O. Okay, here I am going to taking movement about O point will be 0, bottom corner will be 0. Sigma m is equal to 0. Okay, at this particular point I am going to take movement is equal to 0. Movement about this point is equal to 0. Okay, when we consider sigma x, for sigma x, we in reality we can't balance the stresses. It is difficult to make stresses is equal to 0, but we can make the forces is equal to 0, or we can take moment equation for the forces. Okay, but we can't take moment equations for the stresses directly, but indirectly we can take the stress we used to convert in terms of the force. How it will be converted into the force? By taking sigma x into the surface area of this particular plane. If you see here, height of the body, this surface del y, and thickness of this surface will be 1. Okay, when you multiply del y into 1, it will be gives area, and if you multiply this area with this particular stress, okay, it will gives force. Okay, you can get the force from this particular element. Okay, this in this direction. Okay, this normal stress will be acts as force now. Okay, if you see in this diagram, when you take moment about this point, this force is acting negative direction. Okay, anti-clockwise I am taking as negative symbol will be there, and sigma x into del y will be the force into it is acting at the depth of dy by 2. The sigma x force, the force related to this component is acting at the depth of dy by 2. Same thing. And similar another component of x-axis we can see sigma x plus del sigma x by del x into dou sigma x by dou x into del x. Okay, this is also acting in positive direction, positive x-axis direction. That's why I am taking this one as positive, and this total stress is acting on this particular surface having the same area. You can see del y into 1. Okay, you can see the del y into 1. Okay, this is the stress and this is the area, and this is the force. This particular element will becomes force up to del y. Okay, and this del y will be multiplied with the perpendicular distance. Okay, from point O to this force distance. Okay, the perpendicular distance between these 2 points will be del y by 2. Okay, we can see here sigma x is acting at del x by 2. Del y by 2 here, not del x by 2. Okay, and this sigma this stress is acting at the height of del y, and the area of this one del y into 1. Okay, and this stress, this will give force. This force is acting at the distance of del y by 2. Okay. Similarly for this one, y component also we used to take same thing, whereas sigma y is acting in negative direction. Okay, sigma y is acting in the negative direction. Okay, that's why I kept this one as negative. Sigma y into the area of this particular cross section, del x into 1. Okay, whereas thickness is 1. Okay, del x into 1 into leave around from this point to this distance, del x by 2. Similarly for sigma y plus del sigma y by dou sigma y by dou y into del y. Okay, it will be the stress into area of this particular element at this particular surface will be 1 into del x. Okay, it will give us 1 into del x. We can see here, we can see here up to this point it will be 1 into del x, and after that we have to multiply the distance between these 2 points. Okay, from here to here distance will be dx by 2. Same thing I have given here. Okay, whereas the tau yx for the shear stress components, we can see tau yx. Okay, tau yx and tau xy, these two are acting towards the selected point O. Okay, whereas the eccentricity is equal to 0. Okay, in this case forces will become 0. Okay, that's why I am neglecting this particular stresses. Whereas we can see here one stress is acting in this direction, and the clockwise stress I have taken as positive. Okay, the clockwise stress I have taken as positive. Here if you see, tau yx is acting through the center, whereas tau yx at this particular point, okay, tau yx dou tau yx by dou y into del y, this one is the stress, and this one is acting over this particular surface area. If you see arrow here, along this arrow surface it is acting, and the area of this one is thickness for this one del x into del y, you can see here. Okay, this one is the area. Up to this point is the force. When we multiply this force, this particular shear plane is acting at the depth of del y from here O to here. This shear force is acting. Okay, that is the distance of del y. Okay, similarly minus another stress you can see here, tau xy, here tau xy plus dou tau xy by dou x into del x. Actually here dou x will be there. Okay, into del x. This will be stress, and this is multiplied with area del y into 1. It will give the force, and this force is acting at the distance of del x, perpendicular distance of del x. This particular stress is acting del x distance. Okay, similarly we can see the body forces plus which is acting here. Body force will be along the y-axis. If you take y-axis body force is acting in downward direction. For that reason I have taken body force in y direction as the negative, and Fy into del x into del y will be, this force will be carried by this element which is having the area, this one, into this force is acting at the distance of del x by 2. Okay, this is one body force which is acting in the downward direction, and another one is the body force which is acting in inertial direction. Okay, when you apply the inertia, mass of the body is moving some other direction. In that direction also we can see the body force. Okay, Fx which is acting in the positive x-axis direction to del x into del y, the area of the body, volume of the body, and that force is acting at the distance of del y by 2. This particular, if you see here, the body force will be acts in this direction from the center of the body. This distance will be del y by 2. Okay, this is the equilibrium equation. Okay, this is the total balancing moment about the z-axis. Okay, at the point O, we can take this one. After solving this equation, after neglecting the higher terms involving del x and del y, you see here, you can see del square y, this one we used to neglect. del x into del square y here also we used to neglect. Okay, and at this particular case also we used to neglect, and in this case also we used to neglect. Okay, we can get the here equation tau xy into del x into del y, but in second case we can see do square del square y. This one we used to neglect, but we used to keep this one. Similarly here tau xy will be there, negative tau xy, and this one area will be there. Okay, but this term we can see del x and del x, del square x, it will becomes, this will be negligible. Okay, similarly fx we can see, whereas the del square y is equal to 0, and here del square x is equal to 0. After neglecting all these forces, we can get tau xy is equal to del x into del y, and tau xy yx is equal to tau yx into del y into del x. Okay, from at the end you can get the equation like this. Okay, after getting the equation like this, you can finally you can get tau xy is equal to tau yx. Okay, in like manner we used to solve for another two components also, another two direction also. Okay, for three-dimensional bodies also we used to follow same method. Okay, but in that case we used to see another shear stress component also. Okay, that is the different. Okay, and tau x is equal to tau zy, tau xz is equal to tau zx. These are the shear force components. Earlier we have 6 shear stress components. Now these 6 shear stress components has become 3 shear stress components. Okay. After this, we have to derive the equation for differential equation. How we can derive the differential equation? By taking another two equilibrium equations, we used to solve the differential equation for this particular given element. Same thing we have to do. We used to take force directions. Here this one is the force, sigma y into sigma x into area. It will give force. When we use the force equilibrium equation, we used to take forces only. We can't balance the stresses. Here also we used to balance the forces. And here force will be minus sigma x into del y, whereas the del y into 1 will be the area of the body, and del y into 1, it will finally gives del y itself. Okay, when you multiply this stress with respect to with this area, this will becomes the force, and this force is acting in negative x-axis direction, whereas another force component of x coordinate is acting along the x-axis direction. Similarly, y is acting in one y is negative direction, another y component will be acting positive y direction. Okay, but in this case we won't take all these elements. When we consider stresses in x direction, what we used to do, we have to take only forces in x direction only. Okay, for suppose force in sigma x direction, we can say here minus sigma x into del y, and force in this direction sigma x towards the x axis, we can take sigma x plus del sigma dou sigma x by dou x to del x into area of this body will be del y into 1. Okay, del y into 1. These two are the x-axis components. Another two x-axis components we can say tau yx is the towards the positive x-axis direction. Tau yx plus dou tau yx by dou y into del y. It is in positive y-axis direction. That's why here I have taken positive sign. Similarly, minus tau xy. If you see here this tau yx is acting in negative direction, and area of this particular element will be del x. So here whatever may be the area, here you have taken del x into 1. Same del x into 1 we used to consider here also. And similarly, body force is also acting in the x direction. Positive x-axis direction, it is acting along the inertial force direction. Okay, fx into del x into del y, which is equal to 0. This is the one of the equilibrium equation. After simplifying this equation, okay, after simplifying this particular equation, we finally get dou sigma x by dou x plus dou tau yx by dou y plus body force f of x is equal to 0. This is the final final equation we can get after solving this equation. Okay, after solving your equations we can get final equation as dou sigma x by dou x in plus dou tau yx by dou y plus f of x is equal to 0. And here dou tau yx also we can write as, how we can write dou tau yx, we can write as tau xy. Okay, here if you see here they have written this one as tau xy terms. Okay, in terms of tau xy, f of x is equal to 0. A similar expression is written to describe the equilibrium of the forces in y direction. The x and y equations is the following differential equations of the equilibrium. If you see here, if you take forces in y direction are equal to 0, here we can see four forces which are related to the stresses. One is the sigma y in negative y direction, another one is sigma y stress in positive direction, another one is tau xy in negative y direction, shear stress component, another shear stress component tau xy in positive direction with increase of stress. Okay, after solving these four terms, and one body force will be there which is acting in the negative downward direction. Okay, final equation we used to get as like this: dou sigma y by dou y plus dou tau xy by dou y plus f of x is equal to 0. This is the final equation, and this is the final equation which we can get from the y-axis coordinate. Okay, these two are the differential equations of two-dimensional body, 2D differential equations. Okay, we used to use these two equations to solve the two-dimensional problems. Okay, right, and this is about the equilibrium of a 2D differential element.